Okay, hello everyone, welcome back. So I'm going to proceed our lesson with Dalton's law of partial pressure. Okay, so this is the definition for Dalton's law of partial pressure, where it is talking about that the total pressure of a gas in a container is the sum of partial pressure of individual gases which present in the mixture. Okay. For example, given here, in a container, okay, in this container, there are nitrogen gases, helium gases, and argon gases. Okay, so total pressure of this container is equivalent to partial pressure of nitrogen add on with partial pressure of helium and add on with partial pressure of argon. Okay, let's look at another example. Okay, so initially I have this vessel A with nitrogen gas, and this nitrogen gas is 1 atmospheric pressure. Okay, in another container or vessel B, which consisting of argon gases, and this argon gases has a pressure of 2 atmospheric pressure. Okay, then I decided to mix gases in A with the gases in B in a new container, vessel C. Okay, so the total pressure of gases in C is equivalent to partial pressure of nitrogen plus partial pressure of argon. Okay, so partial pressure of nitrogen initially is 1 atm and my argon is 2 atm. Thus in total I get partial pressure or total pressure of all gases present in this new container is 3 atm. Okay, let's look for another example. Okay, so I have this round vessel which is connecting with another round vessel. Okay, vessel A and vessel B. So between these two vessels, there are valves. Okay, this valve is used to turn on or turn off the pathway between A and B. Okay, if I turn on the valve, that means I am allowing the gases in A and B to mix together. But if I turn the valve off, that means I'm going to separate the gases in A, just stay in A, and the gases in B to remain in vessel B. Okay, so assume initially these two vessels are closed by a valve, so no mixing is allowed. Okay, so in vessel A, I have helium gas, which is 750 millimeter mercury. Okay, so and in the vessel B, okay, I have my neon, which is 3 atm. Okay, so the question here is calculate the total pressure when the valve is open. Okay, what does it mean? It means gases in vessel A is allowed to mix with the gases in B. Okay, so back to the Dalton's law of partial pressure, which states that total pressure is equivalent to partial pressure of helium plus partial pressure of neon. Okay, the problem here is helium has a partial pressure in millimeter mercury, whereas my neon is in atmospheric pressure. So different unit, that means you're going to fix with only one unit. So you need to convert helium or neon into one of the units. So let's say we we fix it into atm pressure. Okay, so we need to change partial pressure of helium from millimeter mercury into atm. Alright, so if you calculate, you will get this to be 0.987 atm. Okay, so now we can calculate the total pressure, which is P total. Partial pressure of helium is 0.987 atm plus with partial pressure of neon, which is 3 atm. So the total pressure is 3.987 atm. Alright, so you can also fix the unit for pressure to be in millimeter mercury. If that's so, that means you need to convert this 3 atm into millimeter mercury. Alright, just to let you know, is actually we can use a different formula to calculate partial pressure. Alright, so the simplest one, if you use ideal gas equation, for example, if I want to calculate partial pressure of nitrogen, okay, in a mixture of nitrogen with helium and argon in a vessel, okay, so partial pressure for nitrogen can be calculated by using the ideal gas equation, which is your first option. Okay, so P, partial pressure, nitrogen, multiplied by volume of the vessel. Okay, number of mole of nitrogen, time with the ideal gas constant and temperature. Alright, so secondly, if the total pressure is given, let's say 10 atm. Okay, so that means I also can calculate the partial pressure of my nitrogen by using P nitrogen is equivalent to mole fraction of nitrogen multiplied by total pressure. Okay, what is mole fraction? Just a little recap on your chapter 1. So mole fraction is equivalent to number of mole of nitrogen divided by number of mole of all molecules present in the vessel time with the PT. Time with the PT, so this is your mole fraction. Okay, and then if you want to calculate the pressure, then we're going to multiply with the total pressure. Okay, so that is the second formula. Alright, so let's apply our knowledge with this exercise. Okay, so oxygen and chlorine gas, so oxygen O2 and chlorine gas Cl2 are mixed in a container with partial pressure of 401 millimeter mercury. So this is partial pressure of O2, okay, and 0.639 atm, which is the partial pressure of Cl2, respectively. So what is the total pressure inside the container? So this is exactly the same like our previous example. So you just need to state or fix into one unit of pressure, and I decided to fix it into the standard SI unit of pressure, which is in atm. Okay, so that means I'm going to convert my PO2, okay, from 401 millimeter mercury. Okay, so I'm going to divide with 760 millimeter mercury to get my pressure of oxygen in atm. Alright, so if you press your calculator, you will get the answer to be 0.5276 atm. Okay, so the total pressure is PO2 plus PCl2, which is 0.5276 atm plus with 0.639 atm. Okay, so press your calculator now. Alright, so the final answer is 1.167, and never forget your unit, which is atm. Again, I'm going to emphasize to you the importance of insert unit through the substitution process, because it will help you, or it will avoid you from getting the wrong units at the end of your final answer. Okay, move on to the next exercise. Okay, so if 3 moles of nitrogen and 4 moles of oxygen is allowed to mix in a 35 liters container at a temperature of 25 degrees Celsius. So what will the pressure in atm of the resulting mixture of gases be? Okay, so for this one, there are 2 ways on how you can calculate the total pressure. Is either first, you are calculating partial pressure of N2, and then you add with partial pressure of oxygen that you calculate separately, so you will get the P total. So what formula that you should use is by using, example, P nitrogen volume of the vessel or container equivalent to number of mole of N2 multiplied by ideal gas constant and the temperature, which you already convert into Kelvin. But if I want to make my life simpler, I can just simply calculate the total pressure, okay, by PT equivalent to number of mole total RT over V of the vessel. Okay, so NT is 3 plus 4 mole time with 0.08206 mole per Kelvin liter atm. Okay, so if you convert the temperature into Kelvin, okay, by adding 25 degrees Celsius with 273.15, you will get the temperature to be 298.15 Kelvin. Alright, so divided by the volume of the container, which is 35 liter. Okay, so now press your calculator to get the value of total pressure. Okay, so have you calculated the total pressure? If you calculate, you will get the same answer as mine, which is 4.893 atm. So this is the final answer. Okay, so you have another option if you want to check either this answer is correct or not. So try to calculate the partial pressure of nitrogen separately and partial pressure of oxygen separately by using this formula for nitrogen, and for oxygen you can use PO2V equals to NO2RT, and then you sum up the partial pressure of nitrogen with the oxygen and you will get the total pressure. Okay, so either way, either you calculate using the same method as mine or you calculate separately, you will still get the same answer. Okay, so as an exercise, try to answer this question 8, which is exactly the same or about the same with the example I give to you initially, which is about the gases in vessel A, round vessel A, and then being separated with round vessel B by a valve. And when I allow the mixture, the gases to mix by opening the valve, so you need to calculate the total pressure. Okay, so in this time, instead of valve, it used a different name, which is stopcock. The function is simply the same. Okay, let me guide you. with a little bit more on how to translate this information. Okay, so this is the first flask. Okay, joining by a glass tube. So this is the tube, and this is the stopcock, and this is another glass. Okay, so flask A and flask B. Okay, so flask A is 4 liter, V is 4 liter, containing nitrogen 2.0 atm. Okay, and flask B, which is V equals to 10 liter, and containing carbon monoxide gas, which is 1.4 atm. Okay, so the question asks you to calculate the final pressure in the flask after the stopcock is open. Okay, so this one, you need to calculate the new pressure of nitrogen when the stopcock is open, and new pressure for carbon monoxide when the stopcock is open, and when these two gases is allowed to mix. Okay, so you cannot use PV and RT because we don't have any number of mole, and we also cannot use the formula of pressure equals to mole fraction times with the total pressure, because we also don't have the number of mole information. So the hint here is try to use Boyle's law. Okay, so you're going to use your Boyle's law to calculate the new pressure of your N2 and CO after the stopcock is open. Okay, so if initially nitrogen is in 4 liter volume, but when the stopcock is removed or being opened, now the total volume is 4 liter plus 10 liter, which is equivalent to 14 liter. Same goes on with your CO, which is the V1 should be 10 liter, but after the stopcock is open, so V2 has become 10 liter plus 4 liter equivalent to 14 liter. So I'm going to see you guys in the next video with the discussion on this exercise 8. Okay, take care everyone, stay safe.